Hello everyone. Today we're going to start the discussion on the pipe flow. In the previous chapter, we have considered a variety of topics concerning the motion of the fluids. We have also learned the basic governing principle concerning the conservation of mass, momentum, and energy in the fluid flow. For today topics, we will be focusing on one of the most important topics in the fluid mechanics, which is the pipe flow. We will limit the discussions on the viscous incompressible fluid in the closed conduit, which can be a circular conduit pipe or a non-circular conduit, which is known as duct flow. So there are many applications of the pipe flow. In this slide, you can see pipe with oil flowing inside. This is actually an actual case of the pipe flow um, in refinery unit of Pertamina in Pelaju, Palembang. You can see on the satellite image of the pipe rack connecting two sides of this at the Sungai Komering. We have oil flowing through the pipe, and you can see also there's a simulations of the pipe flow here. Another application is for non-circular pipe, or we call it ducting, is example of applications on the air conditioning um, central system, where you have flowing cold air through the ducting to each of the room. So the purpose of using pipe is to convey fluid through a confined passage, and then it maintain its pressure different from the atmospheric pressures. So it can be higher than atmospheric pressures, or it can be lower than the atmospheric pressures. Wound pipes are most frequently employed to carry fluids over small or large distances. For example, for water distribution network, oil for oil transportations, for the pneumatic system where you use pressurized air to actuate system. We can also have gases or steam for commercial and domestic requirements. And the use of pipe also to transmit power, for example, like the pneumatic previous examples, and also the hydraulic one from one point to another point. Large pipes called penstocks used to lead high pressures fluid to hydraulic turbines, for example, for the power plants, hydraulic power plants. And then also to um, power servo mechanisms on the control system using the oil. So as desired, the pressure in a pipe can be above atmospheric pressure or below the atmospheric pressures. There is limitations to the applied pressures in the pipe flow. Of course, for the upper limit, there is no limit. It's only limited by the strength of the material of the pipe that can hold the pressures, that can hold the fluid flow inside the pipe. However, there is a definite restriction to the negative pressures because there is a phenomenon what we call the capitations. You can see over here, you can actually click the link on the slide that will show you visualization of what the capitation is. So the point is when the pressures in a pipe drop below the saturation vapor pressures of the fluid, for example water, then the water will become vapor and the water vapors can burst and then create a pressure shock wave and also a microjet of the liquid water that can attack um, the component, the mechanical component. It become very abrasive and then it can damage the component, for example, in the valve, in the turbine blade, and there are actually common problem occurring on the pipe flow. There's also vapor lock obstruction to flow, especially for the small diameters of pipe that can block the flow. So therefore, it is necessary to ensure that pipe conveys fluid at a pressure in excess of the vapor pressures to avoid uh, vapor lock obstruction or cavitations. And also, it may also be noted that when a pipe discharges to the atmosphere, then it will be considered at the atmospheric pressures. And also, when a pipe drawing fluid from the atmosphere, then the pressure at the entry can be considered as an ambient pressures. Let's visit back the underlying equations that govern the fluid flow. We consider a fluid flow in a pipe between point 1 over here and point 2. Then this energy equation applies. This energy equation actually represents the energy conservation of the flow, potential, the kinetic, and also the viscous effect of the flow itself. So this term alpha 1 and alpha 2 can be ignored if we have considered as uniform velocity profile both at both points. And also I need to note that it's only applied for the viscous and incompressible steady flow fluid in a pipe. So you may see that this is a familiar equations you may encounter previously by the Bernoulli equations. The one difference is we introduced the term HL over here, which stands for head loss or the friction loss. The friction loss is because of the viscous dissipations um, due to the viscous layer frictions between the viscous layer of the fluid on this case. So our focus on the pipe flow would be in determining what will be the friction loss or the HL value calculated, which depends on several properties of the fluid, also the pipe itself. Okay, now let's consider fluid flow in a pipe. When we have a fluid flow steadily through a pipe of a constant diameters, It's important to note that the average velocity at each cross-section remains the same. However, the static pressure P, noted over here like P1 over here, will drop along the direction of flow. It's because the stagnation's pressure drop due to loss of energy in overcoming friction as the flow occurs. It's because the viscous properties of the fluid flow that create the friction between the layer, so the pressure drop to overcome those frictions. Darcy-Weisbach formula actually give relations between the pressure or the head loss due to friction or turbulent flow through pipe to the velocity of the fluid, also the friction factor and the diameter of the pipe. Those are the important dimensions that will determine the amount of the head loss or the frictional loss of the flow through the pipe. So this slide explains the derivations of the Darcy-Weisbach formula, where here you have the pressure force along the flow, which is represented by the pressure difference times the area normal to the flow. This pressure force is needed to overcome the frictional force due to the shearing at the pipe wall. Using this formula, CD equal to half density times the velocity square times the perimeter. So equalizing equation 1 and equation 2, we come up with this head loss due to frictional head loss, according to the equation 3. If we represent them in form of pressure drop, this will equal to F, a friction factors, times L, the length of the pipe, times the density of the fluid times the velocity square divided by the diameter of the pipe divided by 2. So you can see the pressure drop is a function of a friction characteristic F, the length of the pipe L, the density and the velocity square of the fluid, and then inversely proportional to the diameter of the pipe. So the smaller the diameter, the bigger the pressure drop. The longer the pipe, the bigger the pressure drop. The denser the fluid, the bigger also the pressure drop, and also this is important, the square of the velocity. So the faster the flow is square, creating the pressure drop in the flow. The frictional factors F over here depends on the flow regime. For laminar flow, this is the frictional factor is equal to 64 divided by Reynolds number. But for turbulent flow, it's involving more complex relations. We can use this formula for certain Reynolds number, or we can also use what we call the Moody diagram to determine what's the frictional factors. So as previously explained on the Darcy-Weisbach pressure drop formula, we're going to need frictional factor to be able to calculate the pressure drop. So one way to calculate the friction factor is using the Moody diagram, as you can see on this slide. Moody diagram consists of the horizontal axis is the Reynolds number. The vertical axis on the right is the E over D, where E is the surface roughness and D is the diameter of the pipe. While on the left is the friction factor that we are looking for. So the way we use it is we need to find first the Reynolds number and then pull the line up until you cross the E over D lines, and then you go to the left to find what the corresponding friction factors. Another way to calculate the friction factor using implicit equation of Holbrook equations over here. This is also another way to find the friction factor. Okay, so let's try to put it on example over here. We have a water flowing in a 10 millimeter diameter of a galvanized pipe with a known surface roughness E of 0.15 millimeters, and the water is flowing with a velocity of 5 meters per second. We are required to calculate the pressure drop at 4-meter pipe length. So first steps to solve this problem is we need to know what kind of flow regime that flow inside the pipe. We do that by calculating the Reynolds number using the usual equations: density times the velocity times the diameter divided by the viscosity. Plug in all the number, we able to have the Reynolds number of 4.45 times 10 to the power of 4, which is for flowing a pipe considered as a turbulent flow regimes. The next step is to calculate the E over D, the surface roughness, divided by the diameter of the pipe. We have 0.015. From the knowledge of the Reynolds number on the previous calculation, we can pull the line up until we cross the line of 0.015 E over D, which is this point. From here we go to the left to find the friction factors, and from our calculation it is obtained as 0.045 as the friction factors. Once you know the friction factors, we can use it to calculate the frictional pressure drop using Darcy-Weisbach equations as follow like this. We just plug in all the numbers, and then we can obtain the pressure drop, frictional pressure drop as 225,000 Newton per meter square. So on the previous slide, we have discussed the head loss, or the major head loss that is due to the viscous frictions between the fluid layer and between the fluid layer and the pipe wall. There is also on top of that minor losses in the pipe flow due to several characteristics. So apart from the head loss in the pipe flow due to frictions, the other sources of loss of head are enlargements, contractions, bends, exits, entrance, and also valve over here. So all of them will contribute to head loss or the pressure loss on the pipe flow. Take a look on this figure for the sudden enlargements over here. There is a phenomenon called the separation of flow at the periphery of the smaller pipe over here. And then due to that, we have a consequent eddying motions over here in the corner regions. And they cause the pressure drop or head loss from point 1 to point 2 over here. And they can be evaluated by applying the continuity and integral momentum equations. So applying the continuity equations and the momentum equations over here, we combine them to get equation number 9, and then substitute them into the Bernoulli equation. We obtain the HL, minor loss due to sudden constructions over here. We represent this geometry function in terms of KL, or loss coefficients, which is only the functions of the geometry itself. So when we want to calculate the total pressure drop of a flow in a pipe, we need to consider both the major loss obtained from Darcy-Weisbach equations and also from the Modi diagram, and also the minor losses due to the contractions or enlargement bands and everything to top up with. So let's do an example on calculating the heat loss in the flow of pipe. We have a galvanized iron pipe with the known diameters and then a fluid of velocity of 5 meter per second, and then it has also a globe valve with a fully open at a distance of 4 meters, and we are required to calculate the pressure drop of the section including the valve, which means we have to calculate the major and minor head loss. So we can first calculate the Reynolds number. Over here we obtain the Reynolds number of 1.34 times 10 to the power of 6, which is in the turbulent region, so we have to use the Modi diagram or Holbrook equation to calculate the major head loss. Substituting them into the equation, we can obtain the major head loss of 0.247 meter, while the minor head loss is the loss coefficient KL times V squared divided by 2G. We obtain 12.755 meters. So the head loss total is 13 meter, or in terms of pressure unit is 127,000 Pascal. So from this example, it's also important to note the major and minor actually doesn't represent the magnitude of the head loss. It's just to differentiate between the friction head loss and the minor head loss due to the fittings or the bends and so on.